So welcome everyone to today's Mari seminar. We're very happy we're having one of our own speaking today. We'll have Millicent Cheng from Mari speaking along with Kabir Ahuja. They've been working on multilingual evaluation of generative AI, and this has been a collaboration between the Mari team and the MSR team in India. So just a little bit about Kabir. Kabir Ahuja is currently a research fellow at Microsoft Research India, where he's being supervised by Dr. Sunayana Sitaram and Dr. Manojit Chaudhry. He's primarily working on improving and effectively evaluating cross-lingual transfer in pre-trained multilingual language models. And then, of course, Millicent Cheng, she's a data and applied scientist here at the Microsoft Africa Research Institute in Nairobi. And she's actively working on multilingual evaluations of large language models and enhancing automatic speech recognition systems for the Swahili language. So yes, please take it away, guys.
Thank you, Steph.
Stop sharing.
I'll just quickly share my screen. Just quickly share my screen. 1 sec. So they'll play. Steph, please help me confirm if you can see my screen.
Yes, we can.
All right. Yeah, thank you, Steph, for the introduction. A warm welcome to everyone on the call. Today, alongside Kabir from MSR India, I'm excited to talk about our work on multilingual evaluation of large language models. So this work is the outcome of successful collaboration between Microsoft Research India and Microsoft Africa Research Institute. This work was led by Sunayana Sitaram. And so while Kabir and I will be leading the talk, we have other members of the team, like I've seen Kalika has joined the call, and we are happy to answer your questions. So please feel free to post your questions on the chat for us. Thanks again for joining. I think I'll just go straight to the presentation. Yeah, so while generative AI models, or what we mostly refer to as these large language models, might be familiar to most of us by now, I'll just take a moment to revisit what they are. So large language models are AI systems that use extensive training data to generate human-like text, right? Recently, we've seen these models showing impressive performance in a wide range of NLP tasks, from natural language understanding to comprehension, reasoning, text generation, and so forth. And this is now transforming a wide range of NLP applications. But the question that AI community is asking today is, how well do these models really work on languages across the world? Looking at the data that these models have been trained on, and while we still do not know what GPT-4 has been trained on, if you take a look at GPT-3 and even Palm model, very large language models, they have a higher proportion of English in their training data, right? Bloom, this model developed by Big Science, tends to incorporate other languages. However, English and even other high resource languages are still dominating, right? But 6 billion people do not speak English as their primary language. And so this raises questions about the proficiency of these models in other languages and cultures. And so this is why it's very, very crucial to evaluate them, as performance gain in these models on high resource languages might not always generalize for low resource languages. And so what we have done in MEGA 1 is that we have conducted a comprehensive evaluation of large language models, the models being GPT 3.5 and GPT-4 and Bloom-Z models, on 70 unique languages, on 16 different NLP tasks, to just see how these models perform on various languages. Two, we have compared these the performance of these languages with the current of the state models performing well on these data sets. These are models like Microsoft Turing model, Muriel, to just assess their effectiveness. And three, we've recommended effective prompting strategies for using these models, especially on for the non-English languages. And I'll talk more about prompting strategies, which is the evaluation method that we use for our experiments in just a few. And so in MEGA, we have included a wide range of NLP tasks from classification to question answering, sequence labeling, generation, and even responsible AI, and we've covered 16 different data sets, like I've mentioned, from natural language inference to common sense reasoning data sets, all the way to responsible AI, like toxicity detection, and we know machine translation dataset, which is a dataset that measures gender bias in machine translation systems. In addition, we've covered a wide range of language families, Indo-Aryan and Afro-Asiatic languages being the majority of the languages that we covered. The models that we evaluate are OpenAI models, majorly, and then Blue models. So we evaluate these GPT models without fine-tuning them or hyperparameter tuning, and then we compare them against prompt-based baselines like Bloom's model and state-of-the-art fine-tuned models. For example, the state-of-the-art models for these fine-tuned models that we compare the OpenAI models with are like the Microsoft Turing model, TU-LR, the XLMR, which is the multilingual verb model, NT5, and Muriel, which is a model fine-tuned on Indic languages. And so just to assess this model's performance on these various benchmarks, given that these models might outperform completely the current existing models. I'll now talk about the evaluation methodology that we adopted in this study, together with, which is the prompt approach, and together with the various prompt strategies or settings that we used for our experiments. So we adopt prompt-based approach to solve tasks through in-context learning. And what I mean by in-context learning is, this is the approach that involves providing relevant context and information within the prompt given to the model. Because by doing so, we just try to enable the model to understand the task better and generate accurate responses, right? And so for prompt tuning, we rely on prompt source. Prompt source is a database of existing prompts. It provides a web-based graphical user interface that allows developers to actually create or write prompts in templating language. And we consider 3 different prompting strategies: monolingual prompting strategy, zero-shot cross-lingual, and translate test. And I'll explain the difference in these strategies in just a few. So the prompt that we input to the model, large language model, looks something like this, right? So this is an example of a monolingual prompting. So a prompt consists of 3 important parts or components. One, there is the task instruction. We have the few short examples. We have the test examples, right? If I can start with the task instruction, this provides a description of the task to the large language model. So for a monolingual prompt, for a natural language inference task, a prompt instruction could be something like, you are an NLP assistant whose purpose is to solve natural language inference tasks, right? And then you provide a little bit about what that NLI problem is. And then 2, the other component is few short example. And the few-shot examples and the test examples can be in different languages, right? We call the language used to represent few-shot examples a pivot language. And in all our experiments, we use the pivot language in other cases as English, if not for monolingual prompting. Sorry, and I'll talk about that as well. And target language, we use it to refer to the language for the test example, right? And so few-shot examples, this provides in-context supervision for the model during the in-context learning. And the test examples provide, this is now the input, which we want predictions for that the LLM should do for us. And so these are just different examples of different prompts. So we just looked at NLI, or natural language inference prompt. This is just another example. This is also another example. This XQuad, TidyQA, MLQA, these are just data sets for question answering. So that's a template for question answering prompt. And this is just another example for a summarization task. And you can see all of them, you have the instruction, and then you have a place for few-shot examples, and then the test examples. In all our experiments, we kept the task instruction to be in English, right? As in our initial experiments, we saw that English prompts actually outperformed prompts instructions that were written in native language. So we made a decision to stick to English prompt instructions. Now, I'll talk about the different prompting strategies or settings that we use for our experiments. So I'll start with monolingual prompting. So as I mentioned, the difference is just with the examples for the few-shot examples and the test examples. So in monolingual prompt strategy, we have the pivot language and the target language as the same language. So for example, as the diagram, you can see that the few-shot examples that we provide to the model for in-context supervision is Hindi, and the test example is also in Hindi. And then moving forward to zero-shot cross-lingual prompting. So in this setting, we were having few shots examples that we provide to the model for the in-context supervision in a pivot language. And I've said in our experiments, we use English. And then the input data that we want the model to provide to predict for us, we provide them in a target language, which can be Swahili, Hindi, Chinese, and so forth, right? And so that's the difference. The few-shot examples are in a pivot language, while the target or the test examples are in another language. And so in this setting, what we are trying to achieve is to assess the zero-shot cross-lingual transfer ability of the large language model during the in-context learning. In translate test, which is the last one, here we try to, this is much like zero-shot cross-lingual, only that here the target language is first translated into another language and then before evaluation. So for example, in this case, we will sample few-shot examples to provide in-context supervision in English, and then we have the target or the test examples which we want the model to do the prediction for us. We translate them and we use Bing Translator for this particular task. So I'll let Kabir dive deeper into mega performance analysis. So to give him control, I will just stop sharing and he will share in a moment to proceed with this presentation. Thank you.
Hi everyone. Am I audible?
Yes, yes, you are.
And is my screen visible?
Put it
Yes,
in.
it is.
Yeah.
Yeah, just present and you'll be good to see it.
Yeah.
Yes.
Is
It's
it
all
visible?
good now. Yes, yes.
Yeah, great. Yeah. Thanks a lot, Millicent, and thanks to Maddie to give me an opportunity to present our work. So yeah, I'll continue what Millicent was discussing by the actual results that we obtain when we perform the evaluation. So to start with, I'll just show the higher level results that we get, and then we'll dive deeper into these results. So, but what you see here are the results on different tasks, and we have averaged the performance across different languages to report the numbers here. So we have these different tasks here, and then we have these different models, as Millicent just described. So we first see on average how do these models perform. So let's go step by step in this. So the first thing that we see is the GPT 3.5 models, which you all will be more familiar with, like ChatGPT. So GPT 3.5 models are very similar to like ChatGPT that we use. So these models are like significantly worse compared to the fine-tuned baselines. So here I've just highlighted the GPT 3.5 Turbo model, and I'm comparing it with the TULR V6 model, which is the state of the art on a lot of NLP tasks, multilingual NLP tasks. And you can see in almost all the cases, the gap between the two models is quite a lot. Uh, and let's see the second trend. So for GPT-4, we see the things are much better. So you can see it's still worse compared to the fine-tuned baselines, except for some tasks like Xcopa. So we see that for common sense reasoning tasks, actually GPT-4 model GPT-4 is able to outperform the fine-tuned and other baselines. But on other tasks, it still lags behind. But the gap now is much more less. And also, it goes without saying, but it does obtain very significant improvements over the GPT 3.5 or Chat GPT models. So almost in all tasks, we see very big jumps in the performance. So which is good, but the overall message here is that we still lag behind. Uh, what is the best that we can do in these languages? And last point I'll discuss more in detail in the next slide. As Monojit, as Millicent described, we have these different prompting strategies here that we are evaluating, and this plot basically shows these few tasks show the performance with two models, DaVinci 003 and GPT 3.5 Turbo, how the performance varies when we use different prompting strategies. So if you see the bars with the dots, these actually mean the zero-shot cross-lingual prompting strategy. The plain bars are just the monolingual prompting strategy, and the bars with the dashes are the translate test prompting strategy. So if we see the first trend, let's see the performance trends between zero shot and monolingual, the dotted bars and the plain bars. So if you see, in almost all cases, the two are very close, except a few cases, like if you see for the dataset Xcopa. So if you see in Xcopa, particularly for GPT 3.5 Turbo, there is this huge gap in performance between the zero shot cross-lingual and monolingual. And what we observed when we analyzed why this was happening, we observed that Xcopa in particular has some languages which are extremely low resource. For example, Xcopa has Haitian Creole and Quechua as languages. And when we evaluate them in a zero-shot cross-lingual setting, that is, you give few short examples in English and then give the example in one of these languages, what the model does is it resorts to just say that these are the question is in the language that I don't simply understand. So we see this problem happen significantly with GPT 3.5 Turbo when we prompt them in like low resource languages. But when we do provide some examples in these languages, like in Quechua and Haitian Creole, then the model never actually says that it doesn't know this language and it's able to understand that it's supposed to solve the task in these languages. And that's why we see a greater improvements in this particular case. But apart from that, usually they are quite on par. But yeah, what's even more interesting is the trends that we see between the normal cases, like the monolingual cases, and the translate test. So now let's see the plain bars versus the dashed bars. So if you see the for test set for the data sets where we have like very low resource languages again, like Xcopa, Xstory Close, and Indic XNLI, So the difference in performance is quite a lot between the monolingual and translate test strategies. So in all these cases, we see that translating actually helps a lot. And to see this phenomena more clearly, what I've done in this plot is that we have plotted the relative improvement that we get when we do translate test on a language versus when we do monolingual. So how much improvement in performance that we get. And here what we have done is we have grouped each of these languages into 5 classes. So these are from the earlier work from our group, which classifies languages into 6 classes, where class 5 are the highest resource languages and class 0 are the lowest of low resource languages. So if you see the plot, so the languages which are typically lower resource, there is a very high improvement in the performance over the monolingual case. So, and the overall message here is that if you want to work with very low resource languages with these models, currently what the best that we can do is first translate them to English and then send them to the model, which is not optimal, but that's the state we are currently in. I'll show why this is not optimal, but there are many reasons why this is not optimal. One is our translation quality may or may not be great, right? Especially for low resource languages. The other reason can be that when we are translating, we are actually losing a lot of cultural context. And especially when we are doing generations, we want the text to look more human-like, not like something generated from translation. So yeah, these are some of the issues with translate test. But apart from all these issues, that's currently the best we can do. So yeah. And yeah, I didn't really say anything about translate test in GPT-4 yet. So let me talk briefly about that. So these are 2 tasks. These are X very close and X tasks. So these are like common sense reasoning tasks, which evaluate how well the model can understand like common sense like humans do. Right. So if you see here, like Telugu and Burmese, so the blue bar corresponds to GPT-4 model. And the blue bar with dashes correspond to a GPT-4 with translate test. And it's the plain one is just the monolingual. So if you see on both Telugu and Burmese, we see there is like this huge jump again. Overall, it's GPT-4 with translate test and monolingual, it's pretty close. But for low resource languages, again, the same trend is observed, where translating is the only viable option that we have. And similar trend goes for Xcop also, where for Tamil we see there is this huge jump in performance. But yeah, as I was talking about it earlier, does translate test solve the problem that we have? But the answer is actually no. So let's see this. Yeah. So in this example, XNLI, which is the task that Millicent started out with describing. So if you see like on English, GPT 3.5 Turbo gets around 76% performance, which is like a decent performance on the task. And let's see what we can get with Urdu even once we do translate test. So when we do translate test, the performance improves. So originally it was 49%. When you do translation, it goes to 54%. So there is this 10% relative improvement, but the model is still worse at solving the task in Urdu than it is in English. So we can't just use translate test to solve this problem. So it helps improve the performance, but we don't really get the same level of performance that we get for English, which is like the lesson, the takeaway here. So yeah. And this is just a linguistic comparison of the results that we have. So here we have just in the left, we have grouped the performance with respect to the language families. And on the right, we have grouped them with respect to the language scripts. And we have then plotted for each of the tasks. So yeah, it's a bit hard to read, but let me try to describe what the pattern here is. So these are language families. And if you can see, for most of the tasks, the highest performance corresponds to this pink circle, right? And this pink circle basically corresponds to the Germanic languages, which will include languages like English, German, and so on. So we still see the best performance that these models can get are on Indo-European Germanic languages. And similarly, if you look at if you look at the right hand side plot, again here the here the pink circle corresponds to Latin scripts, and again we see that almost on all tasks the best performance that we get is on languages with Latin scripts. So what this basically says that the model is works better on high resource language families and the languages which have scripts in Latin. But on other like Dravidian language families and the scripts that are not Latin, the performance tends to be much worse. Yeah, so that these were like the overall results we had. But next, what we wanted to do was we wanted to understand why these trends are, why the model performs good in some languages and why it doesn't perform good in others. So the first thing that we had observed was that the model tokenizes different languages very differently. So let me first describe what I mean by tokenization here. So if you have worked with these models, so what we do is we give them a piece of text, right? And the way the model understands the text is a sequence of tokens. You are given a text and it breaks it down into tokens. So one of the easiest way we can think of tokenization is we just break down a sentence by different words. But that's not what these large language models typically do. Instead of doing word level tokenization, they do something called subword tokenization, which is done to control the amount of vocabulary that you have. So what it basically does is it will break the sentence into a sequence of subtokens. So if a tokenizer is of a good quality, it will break the sentence roughly into a sequence of words, and it might break it into like subwords where it makes some linguistic sense. Like in English, it can break badly into bad and ly. So it will the good tokenizer will be able to catch such interesting inflections and won't be just breaking it down without any such motivation. So yeah, so like one of the worst thing that we can think of a tokenizer doing here can be just break down a sequence into a sequence of characters or a sequence of bytes. So that can be considered like as a bad quality tokenizer. So yeah, so that's what we wanted to see, that how good are the tokenizer that GPT models as well as the other models use compared to on different languages. And to measure the quality of tokenizer, what we just do is we measure something called the tokenizer fertility. So tokenizer fertility is just defined as the number of sub-tokens a particular word gets broken into. So let's say I have a word Kabir. So a good tokenizer, I can think of just using it as Kabir, but a worse tokenizer will break it into KABIR, like into 5 tokens. So we create a huge data set of words and we see on average how many tokens like a single word is broken down into for different languages by the same tokenizer. And then we just plot the tokenizer fertility on different languages for different models. So if you can see for highly sourced languages like English, French, and even Japanese, the fertility is very close to 1, which means that it roughly doesn't change. It doesn't break the words overly. But if you move to low resource languages like Telugu, Malayalam, Tamil, which are non-Latin script Indian low resource languages, the fertility is very high, especially for the GPT 3.5, GPT-4, and the DaVinci 003 models. So you can see the fertilities are as high as 10, which just mean that the tokenizer of these models is just breaking these languages down into set of bytes. So this has a lot of so this can be bad for a lot of reasons. One thing is that now we have a much bigger sequence length to deal with, and this increases the cost with which we use the models, as well as it can have other problems that we know that models generally struggle when they have long range dependencies. So this create these problems that we are aware of. But what we wanted to see was that in practice, does this have any effect on the performance that we just observed? So that's what we have done here. So what we have done here is we have plotted for different tasks a scatter plot between tokenizer fertility and the performance that we obtain on a particular task. So different tokenizer fertilities will correspond to different languages. Like English will have the best tokenizer fertility close to 1, which is marked by here. And Tamil in our datasets had the worst, which will be marked here. And then we just plot fertilities of different languages and the scores that we obtain for these languages. And we see for many tasks a very clear trend. And the trend is that we see, like you can see, there is a negative correlation between the two, right? Which means if your fertility is high, your performance tends to be low. So if fertility is high, that just means the tokenizer quality is bad. So this very clearly shows for both ChatGPT and GPT-4, that due to the bad tokenization in these languages, it results in poor performance. And this also suggests an area of improvement, how we can improve these models to perform better in these languages. And yeah, and another factor that's like more obvious than tokenization that can affect the performance is the amount of data that we use for pre-training these models. So in the beginning, Millicent just showed the language distribution for these different models, right? So we saw that for GPT-3, most 93% of the data was in English, then there was some data in other languages, right? So we can plot the different amount of data that we have and see if there is any correlation between the amount of data that we used for pre-training and the final performance that we obtained. So in this case, again, we see a very strong positive correlation for both ChatGPT and GPT-4. That is, that languages which have more pre-training data, they tend to perform well. The models tend to perform well on those languages. And again, this tells us the area of improvement is to have more representative set of training data in these languages when we pre-train these models. So yeah, so this was just mostly about the results and some analysis of the results. Next, what I want to talk about is, in general, when we're doing a very large scale evaluation, multilingual evaluation like this, what are the challenges that we faced and like how we resolve them? So the first thing is that there is like a kaleidoscope of different choices. So there are so many modeling decision and evaluation decisions that we can make, which can start to quickly get out of hand. So how do we choose a prompt, right? So Medicine just mentioned we do prompt tuning using prompt source, but we do so only on English data. But for different languages, there can be different optimal prompts. Then how choice of few shot examples. So in all our experiments, we generally used 8 few shot examples, but could we have used more to improve the performance? And could we select few shot examples a bit differently? So we currently choose them randomly, but are there any other ways of choosing these examples? And yeah, prompting strategies. So Millicent described 3 prompting strategies, but we can have even further. We can go even further. We can ask the model to generate explanations or chain of thoughts and then do the prediction. For English, we know this helps in many tasks. So would it have helped here also? All right. Then in what language we give the prompts and um, can we use external tools? So we just showed that one external tool that we use here is translation, right? We use the machine translation tool and it helps in performance. But are there any other tools? Like maybe we can do transliteration to improve the performance, to make it in Latin script or something which the model understands better. Then what as Millicent mentioned in the beginning, we didn't do a very extensive hyperparameter tuning due to the cost. But are there any sets of hyperparameters that does help improve the performance, right? There's these so many choices that we can't really evaluate all of these choices. But what we have done here is we have evaluated a subset of choices. So the first 2 plots here we have on XNLI and XCOPA, both are classification datasets. And for 3 languages in each of these datasets, we have shown how the performance changes as we provide different number of few short examples. So 8 is what we operate at in the paper, but we see if we had less examples or more examples, how the performance would have been. So the general trend is that there is usually this performance boost when we go from 0 shot to more examples. So you can see there is this sharp increase in the performance, right? But most of the times after 8, the performance tends to get stabilized. So it doesn't really improve, except for Haitian Creole in this case, where it did actually help a lot. But we see that, yeah, it can help improve the performance, but it won't solve the problems that we have. Similarly, we also tried language-specific prompt tuning. So as I mentioned earlier, we were doing prompt tuning on prompt source, but we were only doing so for English and then using the same prompts for other languages. But what if we had done language-specific prompt tuning, right? So here what we have done is on XCOPA dataset, we do language-specific prompt tuning on Haitian Creole and Tamil. So we see it actually helps a lot in Haitian Creole, but on Tamil it actually gets worse. So again, this demonstrates that language-specific prompt tuning is helpful, but it will take you only too far. It doesn't solve the issues that we are facing here. And finally, we also do if we prompt the model to produce explanations. So does that help improve the performance? So yeah, unfortunately, in all our experiments, we didn't see explanations to help a lot. And the performance, sometimes it improves very slightly, like it does for Tamil. But usually, yeah, the performance is still similar to what we get without explanations. So yeah, the overall what I wanted to show with this slide is that there are these many things that we can try, but it seems that the tools that we have currently at our disposal are not enough to solve the problem with multilingual representations in these models. And we need to work on either improving these models or inventing new methodologies which can help improve the performance of these models on these different languages. But it seems our existing set of tools might not be enough. And the other challenge that I want to talk about is that since these models are trained on a huge amount of data, and in case of the recent models, we don't even really know what data went into these models, right? So there is this there's a very real possibility that these models have in some form already seen the test sets that we evaluate on these models on. So we wanted to see, can we quantify this thing, right? Can we figure out to what extent these data sets have been leaked? So in order to do that, since we don't really have the data, it becomes a really tricky problem. And we try to get some understanding of if that's the case by considering three factors. So the first factor that we consider is whether the LLM's knowledge of the data set. So what we here try to do is just ask the model, the large language model like GPT-4 about the data set. What does it know about the data set? So what languages are included in the data set? What is the input like? What is the output like? So we ask the model to spell it out for us, and then we check if what it spits out actually matches the actual test or it's just hallucination. And the second thing that we measure is the test data set for this data set available freely to access on internet without requiring any downloading and all. Because we have some idea that these models use these crawlers, internet crawlers to get their data, right? So if the data is very free to download or free to not even download, it's just lying there on internet, free to access, then it's likely that it was included in the pre-training data. And the final thing that we study is the release date of the dataset. If you prompt ChatGPT or GPT-4, these models will generally spit out that they have their pre-training knowledge cuts off at September 2021. So another thing we check is that the datasets that we evaluate on, were they released before this cutoff date or after this cutoff date? So that's we have done in this table where we have different datasets on which we evaluate on. So we have the green cells indicate that we don't really find any evidence of the phenomena happening according to this metric, and red cells indicate a strong suspicion, and yellow is like partial suspicion. And we see for most of the data sets actually, the model has a very good understanding of the tasks, a lot actually, and many of them are available to download freely on the not download access freely on the internet, and there are only a few datasets which were actually released after the cutoff date. So based on this, it seems the safest datasets here are like X-Story Close, maybe IndieQA, and the last three datasets. So it does mean that there can be some contamination that could have happened, which but the thing that I want to bring out here is even after the possibility of contamination, the performance of these models on these languages is still subpar. So if there is actually contamination happening, in the real life, we can see the models even performing slightly worse or more worse than what we see here. So it still highlights the problem that we are facing here. Yeah. Yeah, so to provide a summary of what all we discussed today, was that there is this significant disparity between the performance of LLMs in English versus non-English languages, especially for low-resource languages with non-latent scripts, where we see the most drops in the performance. Previous generation fine-tuned models currently seem to do these tasks much better on these languages. Uh, And it's often difficult to do better than translating on very low resource languages. It's often much more difficult to do better than just translating the language to English and then prompting the model. And even that, as we saw for XNLI case, is not optimal. And bad tokenization and poor representation in the pre-training data, we do see that they help explain why the performance is bad in these languages, and they provide some future indications of what we can do to improve these models. So yeah, so this was the summary, and going to what are some like interesting future directions that we take up from this work. So the first is to expand the language coverage even further. So as Millicent mentioned in the beginning, we have like 70 languages, but there are like 7,000 languages in the world, right? So ideally, we want to cover as many languages as we can. So we have a better understanding of how these models fare. So we can add data sets from Masakhane or America's NLP, which have like these more low resource languages that we can evaluate on. And the other is the model coverage. So apart from language coverage, we would ideally want to also cover other models. So currently in our study, we just focused on OpenAI models and Bloomsy and other fine-tuned models. But there are new LLMs coming on, right? So like Palm, which is supposed to have better language coverage. So does these models tell a different story or not? So ideally expanding to more models is like the next thing to do. And the other thing, and other very important thing is to incorporate is about the metrics that we use to evaluate these models. So for classification models, we evaluate the accuracy. For for these summarization models, we evaluate the root score. All right. So one thing is that these metrics do not tell us the full story of how well the system performs. And there are these different metrics that we can use to more holistically understand the performance of these models, like calibration, which tells is the model rightly confident about its predictions or overconfident. Then we can see are there any bias in the predictions of the model, right? So there are these different metrics that we can also consider while evaluating the model, which we haven't done so far. And the other thing is that some of the metrics, even for performance, are not really optimal for these tasks. So, like for translation, we use Rugel, which just measures the n-gram overlap between the generated summary and the reference summary. So, which might not indicate how good the quality of a summary is really, right? So, in cases like that, currently the best thing that we can do is human evaluation. And that should give us a better idea about the performance than what actually we measure using these metrics. Finally, we need to incorporate even more NLP tasks. And I'll first talk about NLP tasks. So we did a bunch of data sets, but there are like a lot of NLP problems that we still don't tap into. Like we don't do any semantic parsing data sets. And in generation, we mainly just focus on summarization, but there are a lot of generation data sets like paraphrasing, translation that we can still consider. And since these models are inherently generative models, focusing on that can help us even better understand how well these models do. And the other thing is that these are all NLP standardized tasks, right? So which might not essentially be indicative of the real world usage of these models. So these datasets do really tell us about language understanding abilities of these models. But finally, the way they get used in the real world can be very different, right? So what we would ideally want to have is like more real world data sets which reflect what these models are doing, how the users interact with these models in different languages. So ideally, we would want to evaluate on something like that as well. So yeah, so that's like another direction. So yeah, that brings me to the end of my talk. But I'll be happy to take any more questions. Yeah, thanks everyone for listening.
Great. Thank you, Millicent and Kabir. I think we have two questions in the chat. I'll go ahead and read the first one. So Jackie says, the findings on tokenization are really interesting. Are there practical ways to improve tokenization for low resource languages?
Yeah, so the easiest thing that you can do is when you're training these tokenizers, use data from low resource languages as well. So currently what you do is you take a huge pre-training data, which will have some data from low resource languages, but that will be present in very low quantities, which results in the tokenizer mostly ignoring those tokens. So what we can do is like what other multilingual models do is they'll oversample the tokens from other languages so that you have the tokenizer also more fairly sees those language tokens. And the other thing is you create a bigger vocabulary. So GPT-4 and GPT 3.5 tokenizer is like currently 100,000 tokens, but multilingual models like all multilingual models were like much more than that. So having a bigger vocabulary can help, and also when training the tokenizer, have a more representative data set. And yeah, I can see Jackie's question. Yes, it is trained. We first train a tokenizer and then we train the model. So let's say I want to improve the tokenizer of GPT 3.5 or GPT 4, right? So we can't really change the tokenizer directly because it's what is inherent to the model, and changing the tokenizer means changing the model itself. But there are other approaches, like we can do something like adapters to augment the vocabulary of the models without really changing the model. So there are these different techniques that are around there. But the thing is, we need a white box access to these models to directly apply those techniques.
Great, thank you. And I think Jackie had another question as well. I don't know if you want to read it, Jackie, or should I go ahead?
Yeah, I can see your question. Yeah, so it's like challenges of benchmarking these models. What evaluation might? I think yeah, on English we are already seeing more real world evaluation. So there is this benchmark called Human Eval, uh, 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 Human Eval, which focuses on like more human like evaluation in these models, right? So I think we can expect similar things for multilingual data sets as well. So the thing is that I think on English, people have moved to more complex and more real world tasks. And from these tasks, so these tasks that we just discussed, we used to be very common to evaluate in English itself around 2017, 2018, right? But now on English, we seem to have like achieved the high level, SOTA performance, and we have moved to more complex tasks. But on multilingual, we are still lagging behind those tasks itself. So yeah, I expect we will eventually move to those type of evaluations as well, and it's very important to do so. But currently, it seems that we are lagging behind like some years compared to what we see in English.
Great, thank you so much for that. If there's any other questions that haven't been posted in the chat, please feel free to unmute yourselves and ask the questions. Yeah, we have a couple more minutes. I'm sure Kabir and Millicent will be happy to answer.
Yeah, sure.
Okay, it doesn't seem like there's any. But yeah, if there's any down the line, feel free to just post them in the chat and hopefully they'll be able to get around to them when they have time. Thank you so much, everyone, for joining. A big thanks to Kabir and Millicent for talking us through your work. We had a last minute adjustment because of the holiday, but I really, really appreciate you guys being so great about the reschedule. So yeah, thanks for attending the seminar, everyone, and have a lovely afternoon.